So yesterday we learned about AAA, ACLs, NAT, firewall operations, a little bit demo on all those products, and we did all labs that everyone liked, right? So today we'll start with VPNs. I don't know how much you guys are familiar with it. Let me know like what's your background context on that as we go, and we'll see how today's session goes, okay? So we have a couple of labs lined up as well today on popular demand. So we'll see, okay? So when you think about VPNs, or like have you guys heard, or I know you might have used VPNs at some point to download not so legit files or anything. But apart from that, what do you think is the core purpose of VPN, or what are the keywords that you might have heard with respect to VPN? Connect to a private network. Okay. Secure communication. And anything else? Change the location. Yes, that is the user's perspective when we hear about the consumer space of VPN, right? When you are a user and you're trying to access something else which is in some other location or anything, we do like to think that it's hiding our location. It doesn't exactly do that. It's just proxying your IPs in a way. Okay, so but all the VPN services that you see, right, OpenVPN and other Nord VPNs and whatever you might use on your PCs, that does use the IPs of a different country, so that you're proxying not from your country but a different country. But we have these all keywords that we generally, or customers generally, see in the VPN space. And anyone who's familiar with any of these words or all of these words? Remote access. So what does VIT use as a remote access service for VPNs? Anyone, VIT students? No, not part of pandemic batch. So generally, AnyConnect, has anyone heard of AnyConnect? Cisco AnyConnect? No. Okay, so that is an example of remote access VPN that I have seen a lot of institutions use. IISc uses that, so I'm familiar with that. A lot of companies use that, and we as employees ourselves, we use that. But what you use generally in your end PCs, right, to download files, or what you said, proxying a different country, that is a solution of a remote access VPN. But a more popular solution is a site-to-site VPN that we might discuss in detail today. But any other keyword? I mean, some of it you might have heard, right? Or learned in last couple of days. Encryption, right? And hashing. Okay, so you know public key infrastructure. Okay, all right, cool. So yes, public key infrastructure is one of the core things that we use in VPN that actually secures the communication. Moreover, when we talk about remote access VPNs and how we are actually securing communications over to unsecure media like the internet or public spaces. And hashing and encryptions, they are the algorithmic components of how we are securing those VPNs. So we will get into that. So I won't bore you with all the details what we see on VPN. Basically, VPN serves a couple of main purposes. You want to connect to a private network, or it can be a public network, there's no restriction to that. But you want to connect to a network over an unsecured channel using a secure media. The default media is not secure. You come to this campus, it is not secure. Whenever you're connecting even to the Wi-Fi, it's not a secure media. Unless there is a type of AAA that is getting performed, which uses some secure components, right? For example, you have multi-factor authentication, you have some sort of username and password, or any type of secure component in it. If that's not used, it's an unsecure media. But what virtual private network means is, you are virtually trying to connect to a network that is not in your own LAN. So you're trying to access something that's very far, but you access it proxying that it is in your LAN. Is that clear? Right? You try to access a resource in America just as you would access something in India. That is the goal of VPNs. Corely, the site-to-site VPN we will be discussing. Okay. And obviously that comes with the fact that we want to restrict the usage, we want to secure the communication, we want to secure the devices that are involved in whenever that VPNs are established. So it's a connection-based technology which requires acknowledgement and identification, hashing, encryption. So whatever you might have discussed, right, hashing, encryption, so these are part of public key infrastructure, and we call them, okay, I'll start with here. Yeah, we call them something called confidentiality. Anyone knows what's confidentiality? Sorry. Okay. Yes. So if there is, if I'm sending a message 1, 2, 3, 4, I don't want it to change. I want it to go as 1, 2, 3, 4 itself. There should be no change. If I am talking to you, you should receive the message as it is. Okay? No one should be able to read it. Integrity? Any idea? Yes, kind of. So if I am communicating with you and someone is in the middle, they should not be able to change that communication. So if I am sending you 1, 2, 3, 4, it shouldn't get changed to 3, 4, 5, 6. Okay. Confidentiality, they should not be able to read it. Integrity, they should not be able to change it. Okay. Authenticity, I think that's implicit. If I'm talking to you, I'm only talking to you. Okay. I'm not talking to someone else. And this is called CIA, not the organization, but this is the core principle of any secure VPN communication, PKI communication, or anything. These are the 3 components. In mathematics, we use encryption, hashing, key exchange to achieve all these things. But these 3 are the core components of or what VPN actually uses. Okay. Another thing is an anti-replay. This is specific to site-to-site VPNs in most cases, but this is something a VPN solution provides. So, for example, I want to send you packets, and the attacker who is in between, he's trying to modify these packets. But how will the end device, where the VPN is established or where the VPN is configured, will know that these packets are actually malicious or benign? So they use something called data tagging, where they add sequence number to each data. Whenever, if I am a source of sending these VPN packets, I will send a sequence number to these data. Whenever the recipient of that VPN packet receives that packet, they will map that sequence number to that data. And if it is outside a specific window, it will drop that packet thinking that I already received this packet with a particular sequence number. You know TCP windowing? Any idea? Very similar to how frames go by, right? Whenever you, I mean, some of you might know it, but yeah, similar to that. Basically, you're tagging that data packet with a particular sequence number, and the recipient is responsible to know that that sequence number is a legit and it is in the data packet that I should expect. If it is outside that, I'll drop it. very specific to site-to-site VPNs, but this is a important component that we, when I deal with VPNs in routers, ACs, we do make use of this. Okay. Quickly, encryption, hashing, any doubts or anything? Can anyone quickly tell me what is the difference between encrypting and verification? When do you encrypt something and when do you verify? Or is there a difference, first of all? There is a difference. There are different words, right? No, but apart from that, what is the... No, verification, so don't think of it related to hashing. Hashing is something that's irreversible. It is kind of reversible, but you cannot reverse it directly. For example, if you have a known database of all MD5 hashes, you can reverse it. Okay, we do reverse it in CTFs and etc. There are tools for it. You can do that. But mathematically, the point is, I create a message and I'm sending it through a hashing function, which I cannot get back the same data that I sent. Okay, but why would we want this? Like, where would I want, what's the point if I cannot read the data that I'm sending? Right, there might be some purpose why we are using hashing. The goal is hash matches or not. That's a very big use case of hashing. We actually don't use it to send the data itself, but we want to verify the data is what it was sent or not. Integrity, hashing. Okay, confidentiality, encryption. I sent something, I received the same data, encryption. Okay, what do you think, how verification will come into picture here? Like, I want to verify someone by using signatures. So signatures is something that we use, both these components are used when we talk about signatures, specifically digital signatures that we call it, and I'll cover that in PKI. But yes, so encryption and hashing are the two components that actually make the authenticity part of it. That is where verification comes into picture, okay? Whenever we are trying to send some data that we want them to read, our goal should be encryption because we want them to read. If we want something to be verified, for example, my identity, I don't need to decode my identity, I just need them to verify me. Then we'll think about hashing. Encryption is also used in that, but the main thought is hashing because there's a verification check that would happen at both sides. Clear? Any questions, comments? Okay. So, I mean, we can talk about VPNs for hours and hours, but the types of VPNs broadly that we see today are site-to-site VPNs and remote access VPNs. Okay, and even not Cisco, but any other company that mostly provides solutions for both of these technologies. Okay, and site-to-site VPN in very simple term, like we discussed, two different locations, two different private networks, they're trying to communicate with each other, similar to how they would communicate if they were on the same LAN or same network. Okay, so what could be the, what could be the exchange that you think happens between these two to establish VPN? What is required? Just what we have discussed based on that. For example, this is VIT Vellore and that is VIT Amravati. Okay, and there is some student there trying to talk to a student here. What do you think? How will they establish a communication with each other, or someone else has to do that? Some other device has to do that? What do you think? Can they talk to each other over normal internet? They can, right? No problem with that. Internet, you add them to your Facebook, you can talk to them. But we don't want to do that. There is a very important security file you want to send from here to there. How do you do it? With what we have studied right now, nothing's fancy. Anyone? Encryption will be used or no? If you want a security file, if you want to send a security file. No, see, Alice and Bob is a very, I mean, I'll definitely come to Alice and Bob. You cannot complete a security session without them. But my idea is for you to correlate, yes, we do need encryption. Whenever I'm sending the file, I want them to read. So I need some encryption exchange that would happen. Because you read about AES 256. What else is there? In what type of encryption that is? Symmetric. So symmetric means same key, okay? You encrypt with that key, you decrypt with that key, correct? So symmetric key exchange will happen, but is it possible for me to encrypt that with AES 256 and decrypt it with AES 512? No, right? So they have to establish that we are going to use these encryption keys, right? Similarly, what else? What are the other? What else did we read apart from encryption? Hashing. So in hashing, similarly, we have to do that exchange. Because if you take an MD5 digest and you're trying to compare it with some other SHA-128 digest, will they match? Can you retrieve one from another? Can you detect one from another? You can detect one from another, okay? Depends on the bit size. You can detect one from another, but to establish that I am going to use MD5, you're also going to use MD5. MD5 is a deprecated hashing algorithm, don't use that. But say SHA-128, SHA-256, SHA-512 has now come, right? So you have to exchange that. But one more important thing you need to exchange. What is that? Yes, key you will derive from these algorithms, but I mean, what's the third component we discussed? Remember CIA? Authentication. Identity of the device. If this guy supports AES 256, SHA-512 or anything, it is not enough. This guy has to establish that he is a legitimate VPN device with whom that guy can talk, okay? Amravati VIT can talk to Vellore VIT only if both of these devices are an established VPN peers. We call them peer. So when we say site, peer, they're all synonyms, okay? Because peer-to-peer communication, P2P, you might have heard, right? When we do Windows P2P communication, right? That is exactly how this works, okay? Site to site, LAN to LAN, peer to peer, all these are synonyms. Oh, sorry. Yeah. So these are the broad components of site-to-site VPNs that we deal with. The most basic is point-to-point. Okay, probably. So point-to-point means the same. LAN to LAN. So we write it like this in shortcuts. These are called overlay VPNs because we generally run routing protocols and other services over these VPNs. Okay. I wouldn't go into get VPN. That's a very, very risky topic to teach. But hub to spoke is something anyone has heard Or any idea what it might be? Hub and spoke. Have you heard these terms? I don't see a response. No. Okay. So, okay. I'll probably go here. So, whenever we talk about one site talking to the other site directly, without involvement of any other router in the VPN, that's a point-to-point link. Similarly, okay? I'm talking to Pooja, Pooja is talking to me, that's it. Okay. Hub to spoke is where a single spoke is present, and we extend this to multi-hub, multi-spoke scenario. There's something called DMVPN, where we have dynamic multicast of VPNs that we use for where there are multiple spokes, multiple hubs involved in a, either hierarchical manner or lateral manner. But idea is my main communication between two sites will go through a hub device, where hub is responsible to route that traffic. Sometimes hub can also push policies to different. So the communication we said, right, exchange of encryption, hashing, identity, that would happen to the hub first. Hub will make sure the communication is secure, and then the spokes talk to each other. Okay, in most cases, spokes to spoke communication is not direct, like P2P. Dynamic mesh is just an extension of that. I can talk to the spoke directly once I've established a tunnel with, tunnel, you know this word tunnel? Because I'll be using this word a lot. Okay, basically tunnel is a VPN link. Okay, this link that we see, right? These are called tunnel because there are tunneled kind of analogy. So, yes, any questions still here? Might be new concepts or you've repetitive? New? Okay. Yes, there are logical connections, there are virtual connections. That is the whole basis of VPNs. Okay, we are connecting a logical tunnels to these sites. So Amravati will talk to VIT, Vellore in a logical tunnel. All traffic only will go through that tunnel. No other routes, no other highways. Okay. Okay, so you can go through these slides. I mean, the exchange, it's exactly that we discussed. Confidentiality, two sides talk to each other, they are trying to exchange information, we don't want to change or we want to get the same information back. Integrity, we don't want it to be modified, and authentication, obviously we want it to be verified. These three words should be in your mind if you want to become a cyber security or whatever you want to become, security engineer. Okay, because these three are very, very important. Even the most basic to the most complex things happen with these three components. Okay. So, in broad perspective, VPNs mainly uses these two protocols. These are standard IDF protocols that we use. One is IPsec, IP security, another is SSL. Okay, secure socket layer, right? The site-to-site communication that we saw, right? If a LAN device in a site is trying to talk to a LAN device in another site, we use IPsec. Okay, we don't use SSL. Can you use SSL? Any idea? No, SSL is fast. If you use DTLS, it's fast. But the thing is, when you have a lot of traffic, bulk of traffic going from one server to server. For example, in most cases, what we have is servers communicating with other servers. We don't use or prefer SSL. SSL is a client to server communication, right? Someone has to establish the communication first to reach to the other side. In LAN to LAN, we want continuous communication, right? That is why the preference is IPsec there. Okay. Any questions? Okay. We will discuss these. No, we'll get to that. Yeah. So should I cover these? So, I mean, these are something we discussed. You can go through these. It's for your reading material. But one thing to clarify is that IPsec, the protocol that I spoke about, that itself doesn't provide the encryption, integrity, authentication. It uses them, but it's not a framework that you can use. It's a protocol. So you need some encapsulation over that so that you can use IPsec. Okay, is that making sense? You just cannot enable IPsec, send file. It won't work like that. You need a framework where you can use IPsec for specific traffic. Okay, so I'll get into that. So yeah, IPsec being a protocol suite, and very important, it is not a capital S here. Okay, a lot of people confuse that with IPsec. The RFC is for IP security, which is a single word. Okay, so it is a protocol suite. It can use the encryption, integrity, the authentication part of it, but it doesn't provide a framework for it. So what we do, we use something called ESP protocol 50, AH protocol 51. These are all protocols that run inside IPsec. Okay, and there is something called IKE, Internet Key Exchange. Sorry. So this Internet Key Exchange is the most important framework we have for IPsec. Okay, so because you can't use IPsec directly, you need something that can support IPsec so that the LAN-to-LAN communication can happen. So let me just, so for example, so these are say VIT Vellore and this is VIT Amravati. Okay. Now these two are PCs that are sitting on the end of that tunnel, the logical tunnel we talked about, right? This is the VPN tunnel. Okay. Now, if they want to communicate with each other directly, assuming that they are in the same LAN, VPN has established, which protocol will run between these two? No. So it's not outside VPN, I'm talking about VPN itself. We just discussed, right? So if these two want to talk to each other over this channel, what's the protocol that's going to run? IPsec. Okay, so, okay, I can't run. So when they talk to each other, this is an IPsec channel. Now, obviously these PCs are not directly connected to each other in real world. They go through switch and they actually cannot talk to each other. Right? I mean, is that clear? They will not be able to talk to each other. Why? There has to be a router, there has to be a firewall, there has to be internet and everything, right? So, VIT Vellore will have a server here. It can be a router, okay, or a firewall. Similarly, here there will be router or a firewall. Obviously, that is how these PCs are connected. They can also have switches after this, before the PCs, right? Making sense? So would these devices, the router or firewall, they also have to be part of the tunnel or no? Should they be part of the tunnel? They should not be part of the tunnel. They should be part of the tunnel. Okay? The thing is, IPsec is running between these two LAN PCs. but what is supporting it? These routers will run that protocol which supports it. Okay, that protocol or that framework is called IKE. Okay, this is IKE. So I'll just redraw this. You have IKE, Internet Key Exchange. These devices and then there are PCs. And there is another tunnel. This is IPsec. Making sense? The server devices, or we call these VPN endpoints. Remember endpoints, any endpoint. So similarly, VPN endpoints are the physical devices that actually pass the traffic. Inside that, when they establish IKE, which is, I don't want to go into the detail, but IKE itself also is a bit complicated. It doesn't provide exchange methods also. So it further uses these three schemes. There is Oakley, which actually tells what DH group can we use, what type of key exchanges we can do. Someone said, right, key exchange is important in the VPN communication. Definitely important, because that is how we actually identify each other. Okay, so IKE is a framework. It uses key management system, key exchange system. We'll talk about the key management now. But within IKE, there will be IPsec tunnel. Okay, outer protocol is IKE, inner protocol is IPsec. Clear? IKE will run between the routers or firewalls or whatever device is on the WAN side of the networks, and IPsec will run on the LAN side of the networks. Okay, so where do you think the encryption, decryption of packets starts and stops? From this diagram itself, like in a very logical sense, common sense, where do you think encryption starts and where does it? So this guy is trying to send some traffic to this guy, okay? I can't change the color. What is it? Okay, I got it. Right? So this guy sends traffic to this guy. Assume any IP that it has. So he's sending a ping packet, okay? Where will the encryption begin? Will it begin at this PC? VPN endpoint. So this PC will never actually know it's a part of VPN. For this PC, it's LAN traffic. For this PC, 20.20.20.1 is in its LAN. That's the whole point of VPN, right? You're trying to proxy something that's in your LAN itself. You're trying to communicate with a system that's in the same LAN. It's not always the case. You can go to public sites and everything, but that's the idea. So the encryption begins at the router. Hashing? Same. Okay? Authentication? Same. So the job of this router is very, very important. It will run all the CIA components, it will run anti-replay, it will run the IKE, and it will also run the IPsec. So the encryption begins here, goes here. Where does the decryption happen? Here. Okay, this is important. This interface where the LAN is connected, or whenever the VPN process ends towards the router side, the other end router side, that is where the encryption stops, decryption begins. Okay, it's not just that the encrypted packet goes here and nothing happens. It's like two-way encryption. Okay, hash matches happen here, all good, encryption encrypted packet gets decrypted, goes to the same PC. That is the end-to-end communication that VPNs establish, site-to-site VPNs establish. Okay? Doubts? Comments? Anything? Is this useful? Making sense? Okay. So, all right. So this is something called IKE exchange. I'll just write it down. Okay. Now IKE, identity internet key exchange, has two versions. Okay. When it was RFC a lot of years back, that was called the IKE version 1. Okay. You might have seen in your PC setups, whenever you go to, if you have searched VPN, like you can quickly do that as well, you'll see certain protocols that are available there. There are, if you want to establish an authentication, say for example, there's CHAP, PAP, all these things, right? But if you type VPNs, there'll come IKE v2 setup. L2TP, has anyone heard of L2TP? These are all point-to-point protocols itself that run. They somehow, they are related to VPNs, okay? They somewhat establish communication in a secure manner, okay? So, there are two versions. Now, the popular one that has become is version 2, but IKE, we write it like this, IKE version 1 and IKE version 2. Both of these obviously use IPsec. Now, with respect to packet captures, when you will see packet captures for these protocols, right, you will see something called domain of interpretation. Okay, DOI means it's a mathematical term, but in retrospect, domain of interpretation means which protocol am I interpreting. Now, IKE itself, obviously, it's a framework. It's not a so-called protocol. It's an exchange framework that happens between the routers, the end-to-end routers that we have, right? What it is trying to interpret here? Which protocol is it trying to interpret? No. So, key exchange is not a protocol again. Key exchange is a key term to just exchange keys, as simple as that. But it's trying to interpret one protocol, right? We just IPsec, that's it. So, whenever you'll see packet captures, if you get a chance, you'll see something called DOI in a field. This is your IPsec, okay? You can have other domain of interpretation, there is IPsec v2 also coming. So, to identify the IKE is working for which protocol, that is domain of interpretation. So, for that particular communication, the domain of interpretation for that duration is IPsec. That is what it means, okay? So, what is happening here? I think you learned about PKI, someone said, right? So, what do you think is happening here? Which part is happening here? It's not visible? Oh, okay, sorry, this part. Now, one thing is, before these routers can talk to each other, right, do they need something in their systems to make them use VPNs? Like, for example, VIT Amravati wants to talk to VIT Vellore. Do they need something to know about each other? So that, otherwise what is it? It's not a multicast packet, right? I need to know who I am talking to, correct? So what do you think from this they're trying to establish? Identity. Okay, they're trying to establish each other's identity. So there are two ways to do that. One is a pre-shared key. Any idea? Think of it as a password. We both know the same password. Only if we know the same password, we will be able to establish the connection. Okay, so we don't exchange the password. That is also a misconception. You will not be able to exchange the password in a communication. Because if there is an attacker and he has your keys, they will get the password, right? But whenever you go to a configuration, and this happens in real life, if I am an admin from VIT Vellore, I will actually call up the guy in VIT Amravati and say, you know what, I want to send this secure file. Before that, this is the passcode or this is the password that we are going to use when we establish the VPN. So that is actually a string which is called a pre-shared key. Okay, something else is written, PKI. So similar to this, what would be what could be another way to identify, authenticate? And this happens before even you go and exchange the proposals. Certificates. Okay, PKI is public key infrastructure, certificates. Why certificates? Why just not stop at PKI, PSK? No, that you will do in proposals, right? There's a proposal section for that. Yes. And in real scenario, passwords do get compromised. Even if you are exchanging it over emails or anything, and it is an unsecure method altogether. We are going towards passwordless encryption, passwordless use, the authentication part of it anyway. But more importantly, if you want to establish your connections with 100 other routers, or say VIT Amravati and other VIT MP and all other different colleges, right? Not just VIT, but VIT to some other college. You need a common authority that can say, you know what, all of you are legitimate VPN endpoints. You can exchange information with each other if you exchange the correct protocols and stuff. But identity is something we can provide to you. Making sense? For example, everyone got identity cards. Some body or some organization is what gave you the identity cards, right? You didn't get ID card from some other room, no, right? Similarly, now you can communicate with each other if you exchange the right proposals. So everything comes later. First, you need to establish whether you're using certificates. If you're using certificates, who is the issuer of that certificate? Okay, even only if when all the certificates have either a common issuer or we use a term called trust, very important term in cybersecurity. When you establish the correct trust, then only you will be able to establish or configure even the next part of things. Clear? Doubts? Questions? So this PKI, we often to refer this as, this is obviously the public key infrastructure, but these are certificates. Basically, using public-private keys or asymmetric, the asymmetric keys to establish your identity with each other. That's the goal. Okay? Two ways. Either you give on call, on email or anything, you give draft of your configuration and you give a pre-shared key. It's pre-shared and then you proceed with configurations, or you say, I'm not going to even give you any information about a password or any string, anything, but I have a certificate. Can you trust that certificate? If you trust that certificate, create the VPN. We'll proceed creating the VPNs. Clear? Then what happens? Then the key exchange, key management, everything comes into picture. Okay, let's see if we have, okay. Yeah, in broader perspective, what happens? You gave your identity already, okay? So it's not like you exchange the entire certificate beforehand, but I'll come to that, what exactly happens. But assume that you have all the certificate requirements that you might need, then protocol and proposal exchange happens. By proposal, we mean a token of message that has all the algorithms that each of these devices will use. So it is written like this. Sorry. IKE proposal 1. So first proposal will have, say, AES 256, SHA 128, and the key exchange algorithm. You know DH you know, right? If you element key exchange, that happens. Do you know it happens in groups whenever they're configured? Group 14, group 21, group 5. So basically, instead of giving the raw algorithm to each other and trying to figure out which bit size would be used to exchange the protocols, we club them into groups. Okay, so DH group 14, for example, would be equivalent to some bits of data or the key exchange algorithm. That's the size of the key exchange that is supported. So we have group 5, group 14, group 19, and they're all equivalent to some size of the key exchange. So you exchange that as well. So basically you are telling, I will be using group 14, will you also use group 14 or not? So my proposal, this will have, say, group 14. And there is something called lifetime, because obviously you don't want the VPN to be perpetual, right? There is a limit, time duration, through which the IKE establishment will happen. When that expires, a reconfiguration or a reconnection happens from either of the sites. Okay? Good so far? Okay. And once the exchange happens, this is the outer part of the tunnel. You have the IPsec establishment between the LAN. So, now for example, we have these devices, right? And here there is PC to PC. This was 20.20.1. This is 10.10.10.1. This is sorry. Okay, these two routers are trying to establish the VPN, and these are the two PCs connected to the routers. So the proposal exchange will happen here. Okay. Once the proposal exchange happens, we also need to know which PCs are we talking to, right? You can choose to keep any. We read ACLs yesterday. There is any. There is source and destination, specific, extended ACLs, right? So we mainly use extended ACLs for this purpose, because we want to know which source is talking to which destination. We don't want all the traffic to go through the tunnel. If you want, you can. But when you are being specific, so when IPsec exchange happens, it again will use these proposals. Okay, it will again use encryption. It will again use hashing. And it will use keys that are derived from the IKE exchange here, the key exchange that happens, get to that. But Once this is established, it wants to use encryption and hashing mainly. So why is that necessary? Why can't we use this? Like we already are exchanging proposals in the outer layer, right? Any idea? So we exchanged the encryption, hashing, all algorithms here, right? So once we have the IPsec, we are trying to establish at this point. So why do you think we need again the encryption, hashing, another set of basically the proposal exchange that we do? Yes, for the actual data. So these exchange, remember, are happening here. This is to establish the identity of this guy, not this guy. Okay? To verify this guy and to have a secure communication between this device. But when you want to see which is the endpoint that I'm talking to, we cannot create identification for each endpoint, but we want encryption and hashing there to use whenever we are trying to send data communication. So very important lingo in networking, control plane and data plane. Are you aware of this? No. This is control plane. Anything that gets exchanged, be it any protocol, any type of traffic that happens between network devices, not endpoints, that is called a control plane. Anything that happens between endpoints, that is called a data plane. So you know data bus is there, right? In the architecture we have data bus, all that. So that data bus, whatever it's carrying between endpoints, that is data plane. So to secure the data plane, we'll use IPsec. To secure the control plane, we're using? No, I mean, what's that encryption? Just discussed, right? We're using IKE. Okay? Clear? So, IKE. Sorry for the bad drawing. Is the best I can do. IPsec data plane. Okay, making sense? So IKE works at, okay, I'll ask you instead. What do you think? Where should IKE be placed in the IP stack, TCP IP stack? At which layer do you think it might be more suitable? There are network devices, most likely security devices, firewalls or secure routers or anything, and they're trying to establish a communication. So which layer do you think suits best? Data is what, which layer? So at layer 2. So do you think any MAC or anything is getting exchanged? MAC address? Will you know the MAC address of the device that's connecting? No. Think about. What's the next? What's the next layer? Network layer, which is IP layer, right? Can you send all the applications through this layer? IP layer. You can do the routing, that's fine. Okay. One thing is IPsec, if you recall this, yeah, this diagram, right? Come on. These ESP I mentioned, I'll come to that. Recall and remember, this actually uses ESP to actually establish this encryption, hashing this. Okay. This is portless. This where did I write? Yeah, this. This guy is portless. So it needs someone to carry it between these two devices. This is actually the most important protocol, but it's encapsulated within IPsec. It is part of IPsec. Okay. So there is protocol 50 and 51. Okay, ESP. So if it is portless, it needs something to get carried, right? So where do you carry the ports? Come on, you should know this. Which layer carries the ports? What is above network layer? Transport layer. So the IKE exchange that happens, it happens at the transport layer. And the standard port that it uses is UDP protocol 500. Okay? There is another variation of IKE, or why we would want to switch from 500 and is because of a NAT problem that we faced, and the other port is 4500. These two are the most, these are the standard ports, just forget everything. These are the standard ports that you would use for IKE. So if you want to establish IKE and you have a, say a network blocker here or anything, or ISP which is very stubborn, it doesn't allow anything. Which ports need to be enabled? And something's portless, you need to carry it. This protocol, ESP, you need to enable that ESP, protocol 50, okay? These three are very important for any site-to-site VPN. If you establish in your lab device itself, if you establish between offices or anywhere, you have to enable these three protocols, these three ports whenever you are trying to establish VPN. 4500 is optional, only used when there is a NAT device in between. For example, I don't want to use 1.1.1.2. I have some other IP. This is a private router. Remember the diagram yesterday? Edge firewall, edge router, and a private router, private firewall. I can have VPNs from private routers and firewalls also, right? So if I want to hide that identity, I would be using NATing. If I want to use NATing, will this guy know that which identity am I using? But it has to know. Otherwise, whoever has any other NAT device will NAT that IP and come as a genuine. To recover from that or to address that issue, there's something called NAT traversal that happens for IKE. And it cannot happen on the standard port 500. That is why once these two guys establish that there is a NAT device in between, and that is where the hashing also is used. A packet structure happens, source IP, destination IP, source port, destination port. Hash is calculated on both sides. If there is a hash match, would there be a NAT device in between? It's actually a pad device that's in between, but no. Then we wouldn't use the 4500 port. But if any of these guys are behind a NAT device, IP, source port, destination IP, destination port, calculated, hash is calculated, hash doesn't match, these two guys will establish, the other guy is behind a NAT device, we cannot use 500 port anymore, we will move to the 4500 port. Clear? Too much? Okay. Now, if you look at the screen as well, there is a main mode and a quick mode, okay? Main mode is the IKE exchange we talked about, okay? Between the VPN devices that we exchanged, right? The VPN devices are exchanging proposals, identity, what they are going to use. Okay, expand the first packet. What are all the layers that you see? Do you see 500 anywhere? Everyone opened the PCAP? IKV1.pcap file from box folder. Okay, first open it. Sorry? Destination is?
You can see 500 around destination and source code is
Yes, yes, yes. So assume the first packet. Open that packet, open the Internet Security Association Key Management Protocol. This is ISACAMP. This is the full form of ISACAMP. This is again, IKE is a framework. Inside IKE, there are key exchange and key management protocols. ISACAMP is the one that's used in IKE v1. Okay? Open that, expand that. What do you notice? There is something called SPI. Okay, even if you forget anything, just remember inside to side, two things are important. Key exchange and security association. Okay? We'll cover both. This SA you say, right? You see here on the screen. This is security association. Everyone opened the PCAP? Right. So you notice something, initiator SPI. That is a nonce or a random initiator cookie. You know cookies, right? Cookie ID gets generated. There's a source cookie, destination cookie. Why do you think the responder SPI is 000? We don't know if the other guy even supports VPN or not. Okay. IP routing is there, ports are open, everything is fine. When I am the initiator for VPN, I send that traffic, the first SA proposals. Okay. Expand the payloads, the security association payload. Do you see domain of interpretation? What is it? IPsec. Which means I'm going to interpret anything that IPsec is exchanging or IPsec is in the packets. Scroll down and see there should be a proposal list, right? Do you see payload proposal 2? And then payload transform. Just keep expanding the CLISH symbols, okay? These symbols, the PCAP. These symbols, if you expand, you'll see the packets. Do you see encryption algorithm, AES CBC? Key length is 256, right? Authentication method is pre-shared key. If it is not there, that will be RSA. That's the most popular signature for certificates. So if it's a certificate-based exchange, identity exchange, it will say RSA. And then there is hashing algorithm and there is group description. Group description is equivalent to DH group. The Diffie-Hellman group, which is used for key exchange. Okay. Now, if we go back and assume that this guy has sent, so that message that you saw is MM1. Main mode 1. Okay. I'll point here. So we are done with main mode 1. It sends, do I support this? Do I support this? Do I support this? All these algorithms, it's sent to the responder. So always whenever initiator is sending the first request, okay, the responder SPI is set to 0 because we don't know if they support, if they have a mismatch. If there are legit device, we don't know yet. We don't know where to find the guy. We have the configuration for them, but we don't know if they're open to communication or not. That is why the responder cookies or SPI is set to 0. It comes to responder. Responder says, you know what? Whatever protocols you have sent, among these, the first match is for these set of IK exchanges, the protocols. Remember, proposals we are sending, and proposals is something we have to accept and send back. It's an acknowledgement thing. Unless they send us a proposal chosen back, VPN will not establish. So the VPN can break at any point in these. If this fails, it will break. If this fails, it will break. Okay, and then again you have to start from main. You cannot resume from the other side unless it's a retransmission. Just like any protocol retransmission happens, it happens for some times. After that, we start again from main mode message 1. So now when you look at the responder, the second packet itself, again expand the ISACAMP. What is happening? Why is the responder SPI 0 there? The second packet. Go back to packet 1 and see the SPI value, and come back to packet 2 and see the SPI initiator value. Are they same? No. That is why the responder is 0. Because it could happen that the initiator sent request to the responder didn't get the packets. Since both of the configurations are open, the ports are open, they're trying to communicate with each other on these ports. So they're trying to send packets to each other. It can happen that they fail at the first packet itself, communication itself. Okay. But if you come to packet 3, let's see what's in packet 3. So packet 3 has, what's the responder SPI? Is it 0? Is everyone following? They're able to open PCAPs. You are at the ISACAMP. Yeah, it's not 0. Why? And who is the responder and initiator in this case? You can tell the IP, the last IP, .2 or .4? .2. Sure? It's .4. Look at packet number 2, the initiator SPI. Look at packet number 3, the initiator SPI. Are they same? Packet 2 and 3, not 1 and 2. So who is the initiator? Who sent the packet to? .4. So .2 replied to .4's first packet. So this guy is .2. Okay? Now, interesting part. We established the proposals that this is what we are going to use. Okay? Now comes the part where we'll use the Diffie-Hellman. So here we send our public key. We are not using certificates, we are using pre-shared keys. But still, we'll need asymmetric encryption. Why? Very simple answer. What have we done? Why are we using DH here? Why are we not using AES here? Who is speaking? Sorry? Still unencrypted. you can see the contents of the packets, right? In Wireshark, if you're seeing contents of any packets in the info field, like you can open the field and you're able to read what is the content of, that's unencrypted. So, to establish the identity part, does symmetric encryption work? No. Be it certificates, pre-shared key, password, anything. That is why we need key exchange happening here. Okay? So, Diffie-Hellman is the key exchange method we use. If we are using certificates, it can be RSA, ECDSE, ECDSA, anything. Okay? That is why in the first proposal, we sent the DH group we are going to use, the bit size of the DH we are going to use, so that when we exchange this, the initiator again sends the third packet. He will use the pre-shared key. He will add the AES 256. Let's assume whatever the key exchange was. Okay, can you tell me which are the proposals that got chosen? Quickly. Which packet would you go to find this? Packet? No, you don't have to go there. So first two, so SA exchange happens between first two packets. It cannot happen out of order. Okay, I cannot happen out of order. They're all continuous exchanges. So in the second packet, we sent the proposals. We were the initiator, we sent the proposals. .4 device. Okay, this is, what is this? These are IPv6 addresses, but we'll just, okay, remember this. Go to the third packet. See, wherever we saw the first responder cookie, that is your MM2 packet, right? That is the immediate reply for the IK exchange first packet. Is that not intuitive? Is that clear? It is all connection based, okay? First packet goes to from 4 to 2, 4 to 2, 2 to 4 replies. Yes? What are the algorithms we see? What are the chosen algorithms? Remember, the responder will choose the first matching proposal set that it gets from the initiator. The initiator, if it has 100 policies, proposals, it's called, like, you can interchange the terms. For example, it can have proposal 1 saying AES 256 but SHA-1. Second proposal can say AES 128, SHA-2. And it can send all proposals that it has, the initiator. Responder will choose the first matching proposal that it has in its configuration. So you have to configure here, the pre-shared key, here before coming to this stage. This guy just initiates the communication using those proposals, right? Clear? Puja. Okay, so MM3, which packet is MM3? Extend हो रहा है? Okay, I think we can use this as well to understand. Just Just understand. See, you have the public key value, okay? You have the nonce. A nonce, what is a nonce? It's a very big random number. Just assume that. So a nonce is created using your pre-shared key, add encryption to that, add your hashing algorithm to that, and add another prime factor to that. You do operations on that value, and then you create something called the key exchange payload. Okay, and a nonce value, sending it separately so that this guy knows whether that nonce is matching with me or not. Okay, this guy receives that packet, he sends its own calculation to that guy. Remember, we are not exchanging the pre-shared key. The whole point is, I don't want to send that message to you, right? But we create encryption and we hash it and we send the hashed value. The idea is, if the hash matches here and here, we generate 3 keys, system keys. Okay, those 3 keys are the one that encrypt the forthcoming messages. Okay, that's an auth key, that's an encryption key, and that is an identity key as well. Okay, we get 3 keys. We still don't know if this guy has the same key or not. You'll not know. These are all local derivations. Okay, so now they are just exchanging in the 3rd and 4th packet. This is MM1, MM2, MM3, MM4, MM5, MM6. Okay, MM3, did this guy receive any acknowledgement? He received a message. Okay, this guy sends his own set of calculations, the hash and nonce, okay, the DH key exchange hash and a nonce. This guy sends back its hash and nonce. Then using these, they derive the symmetric keys or the system keys. We call it the 3 keys that I said, right? Those 3 keys are the one only if they match on both sides. We still don't know if they match or not. Then the establishment of VPN can happen in the forthcoming. So this is all unencrypted. We can see the hash of, you can see in the packet captures, right? Go back to MM4 message, MM3 message, packet number 4 and 5. Look at the content. Do you see something called nonce data? Do you see something called key exchange? Yeah, those are all public values. Unencrypted. But can you decode it? They're hashed. That is where you can map it, right? Because they use the hashing algorithm, they got a value, and that value they will use further to derive 3 keys. That keys will come at the end. Go to packet number 6 and 7. Interesting. Packet number 6 and 7. Encrypted. Right? You're not able to see any hash values or anything there. It just says encrypted data. So what happened? They derived keys on their sides locally and they decided to encrypt the further packets using those keys. Now, if key 1, 2, 3, key 1, 2, 3 matches on both sides, then only these guys will be, so if this guy sends, he will be able to decrypt this packet, okay, or rather not this packet. Do you see S key ID, right? That S key ID is whatever is established and derived. He will use this key ID to decode this message. if they understand, if the responder understands that the message that was sent in the 5th packet, I am able to decrypt it, I am able to identify the device, I am able to establish the fact that the keys are matching, I can understand the data inside, it sends the last packet, and the hope is that this guy also can decrypt it with using the same keys. So we derived at the same conclusion without sending the actual information itself. That is the beauty of these VPNs, right? You never exchange your pre-shared key. It actually, it's not Cisco. If, for example, pre-shared key is Cisco, this is not hash of Cisco. Okay, this is not hash of Cisco. You used Cisco, you put encryption on it, you put hashing algorithm on it, you calculated nonce, you calculated the DH group, and you send that information to this guy. Because he also had Cisco configured here as the pre-shared key, he was also able to derive the same set of keys. They exchanged it and they now can establish IPsec. So this is where the identity of the device also goes into the picture. So if you have certificates, this exchange will have a certificate exchange. Otherwise, what will happen is by default the host name or the IP address of that, remember the 1.1.1.1 device IP, that is what is exchanged in this. So your local, this key identity, SA and ID1 you see, right? ID1 means the identity of that device. An identity can be IP address, can be host name. If it's certificate, it's subject name. If it is pre-shared key, it's not the pre-shared key. Remember that, okay? It's the identity of the endpoint, not the identity method, okay? In certificates also it can be host name, it can be FQDN or any identity from that box. Clear? Now if you open, so you see quick modes, right? Quick mode packets, remember? We had quick mode here. Now this is where the IPsec exchanges happen. Basically, you say here, okay, I got the 3 keys. Now how do I verify or how do I send data traffic to my endpoint, my PC? This is how you establish the tunnel for that. You say, what is the PC I am going to talk to? What is the PC I am originating the traffic from? Do you see proxy IDs? Are you looking at the PCAPs? Will you be able to see it in the PCAPs? Then why are you looking at the PCAPs? In PCAPs, all you'll see is encrypted traffic, okay? Now, what did I say? Key exchange and security association. Remember these 2 things. This is what makes tunnels. We had the key exchange, okay? Now it's the security association that kicks in. I'll open the... So encapsulating security protocol, ESP, that is present here, it will create a database on the initiator and on the responder side. Okay, there is a database where I create an inbound SPI, I create an outbound SPI. So, I know you'll get confused. looking at the packet captures. All clear till now? Too much information? Now, we established the fact that my identity is verified. We are good to go. So now, this was control plane. This is also control plane, okay? Because you are exchanging still with the initiator and responder. Remember that, okay? You are establishing this so that at the end of this is where your data plane actually starts. But to encrypt this data plane, this quick mode is what is used, okay? To encrypt the quick mode, you were using this layer, tunnel within tunnel within tunnel, thing like that, okay? In quick mode 1, what you will send is, you will again send the hash and nonce value that you get from the keys, because remember when I said proposals, you also send proposals for IPsec, correct? You send proposals for you send proposals for IPsec also. So at this point, you will see I'm going to use AES-256 again, but for what traffic? For the actual traffic, right? Before, when we did IKE, it was to encrypt these packets. That is the exchange. So there are two layers of exchanges that happen. In the quick mode message 1, you have the proxy IDs. This proxy ID is the IP of the source and destination endpoints that you are going to use IPsec for. Remember the PCs connected on the routers? Those IPs of the PCs. And because it's encrypted within IKE is already getting exchanged, verified, and you will not be able to read these IPs. That is how you actually create private networks, communicate with each other. Because the private networks don't want this to be routed over internet. You're not routing anything. At the IP3 layer, go back to the packet capture, see any packets, pick any packet and see what is the network layer IPs there. Do you see any other IP than .2 and .4? Are you seeing any other IPs? No. Because the exchange is happening between the, not the endpoints, the devices. And that is why for layer 3 routing, layer 4, all layers, the packets are between these two. You will not be able to read the private IPs that are there. Okay, that is the whole point. Okay, now once you exchange, what are the IPs that I am going to talk to? PC1 and PC2, right? Then you realize, okay, what are the exchanges that I am going to do? That is where the security association kicks in again. That ESP protocol that will actually send the data traffic will create a database on both sides. Okay, I'll just. So this database will have one inbound and one outbound SPI. You remember, you saw in message 1 and 2, initiator and responder SPI, remember? When you go to ESP packets, if you look at the ESP, there is in info, there is an SPI value. That is the security association database that you're creating for ESP. Okay? Now, if you are an initiator, for example, you have those PCs connected, 10.1.1.1 or 10.10.10.1, 20.20.20.1, right? What will be the ESP of inbound and ESP inbound of initiator versus ESP inbound of responder? Will they be same or will they be different? What should it be? Okay, what is the most common operation in CIA that will happen at the actual? Remember, this is data exchange, data plane, actual traffic. So, I mean plain text because this is the actual data plane traffic that is there. It is still encrypted when you look at the packets between these two devices. Okay. What is the CIA? Which CIA operation will be happening here? Sorry. Confidentiality, meaning encryption. So if you want to encrypt, will it be symmetric or asymmetric? Symmetric. So till this point we did all the mehnat of getting the asymmetric identity, ye wo sab kar liya. Now we want only communication. We are done securing the tunnel, now we'll just do packet exchange. The data plane happens. But if someone wants to look at that packet, should they be able to read it? Still it's under a tunnel. That tunnel is created by ESP. But if I want to map what traffic am I sending versus what traffic am I receiving, there should be some differentiation, right? Or there should be not. That's why we have the SPI database, so that if I am a router and I have 100 routers that I am connecting to via VPN, how is my traffic for VPN using ESP different from the connection that I am doing with router 1 versus I am doing with router 2? And if I am looking at the packet captures in between on WAN, unsecured channel, how do I make sure that there is bidirectional traffic that is coming? There are other use cases as well, obviously. The whole point is on the routers we have a database, the ESP database that we have, that are responsible to differentiate between what is the incoming packet versus what is outgoing packet. And the actual SPI index that is on both the sides. They should match, right? For one particular connection, the responder, if you look at the packets again, the initiator and responder SPI values are same throughout. That tells us this is single communication. If the communication breaks and it re-establishes, will the SPI values be same? No. Makes sense, right? I mean, it's logical to do that. So, if we have the ESP database where we are saying that, okay, this ESP database is for 10.10.10.1 and 20.20.20.2. Same here. Because we exchange the same proxy IDs, that is how the tunnel established. If the proxy IDs are different, tunnels won't establish, right? All ciphers, all exchanges should be same or at least negotiated to a common value. That you need to remember, okay? There are a lot of complications that happen obviously in these as well, but the core idea is this. So, what do you think? Is this inbound value same as this inbound value? The inbound value, is that not clear on the board? So, ESP has a database which is taken care by SPI. So, 1 hex values will be there, hex1, hex2, so these are all SPI values. So, there is one inbound, one outbound. Okay, on the responder similarly. So, what is the connection between these two SPIs? Should they match inbound to inbound, outbound to outbound? Should my inbound be your inbound? Is that making sense? Yes. Okay. If I am, why is that I mean, why is that the case? Why did you think that's the receiving the data? Encryption. That's the most important factor that's happening at this stage. Okay, forget hashing anything. We are at symmetric. We just want to encrypt the data and decrypt the data back. So if I am encrypting with one SPI, the decryption SPI of the other device should be the same. That is when the same data will match. And in return, whatever is the inbound SPI of the responder will be my outbound SPI. Okay, so this is how it is done. Oh, sorry. It is this. Okay. Very pathetic drawing. You can draw better on your notebooks or wherever you're drawing. But yeah, do you want me to get into more details, or this is too much information? So okay, yeah, this is important. Okay, we had the encrypted data. This is our ping, HTTP, any packet between that 10.10.10.1 and 20.20.20.1 PC. Okay, the actual traffic that is going. An IP header gets added of ESP. Okay, this will be protocol number. What's the protocol number for ESP? 50. Good. And here the IP address will be 1.1.1.1 and 2.2.2.2. Or I think we have gone off track with the IPs, but you get the idea, right? These are the VPN devices, the outer layer. Okay? Clear? Cool. Now there are different modes in IPsec, because IPsec again itself is not the actual, it also encapsulates, it has ESP, AH, so it has different modes, tunnel mode and transport mode. They are used for different use cases. Main difference being, and by default we use tunnel mode, is because if you open the ESP packets, you still don't want to look at the private IPs that are available. Okay? That is the tunnel mode. When you use transport mode, the IPs of the PCs that we talked about, the endpoints, they will be visible. There are use cases for transport mode as well. They're lightweight, they carry the traffic faster, and so on. Okay. Just a recap on what we established till now. No, it's overwhelming. But remember I said IKE v1 came a lot of years back, the first version. The new version is called v2. That's it. And that is aimed to, so there was a problem with IKE v1 related to MITM. So to address some of the issues, to address even anti-replay issues in IKE v1, they said we want to reduce the number of packets that are getting exchanged. Because a lot of times in IKE v1, if that, since I said it's an ACK based, if one fails, it will still try to establish. If it doesn't, then again it will go back to the first message exchange. Okay. So to reduce the number of messages that are used in IKE v1, IKE v2 was established, and it is the most popular. So if you go to that, if you go to your PC and type VPNs, I said, right, there is a Microsoft VPN you want to establish, or I think it comes as a Windows VPN, not sure. You'll see IKE v2 there. That is what is used for even remote access VPNs. Just remember, this was all side-to-side VPNs, okay? What we did right now. LAN to LAN, peer to peer, side to side. This is how the normal exchange happens.